So when we were talking about the temperature distribution within a pipe, so we have a pipe, and we know that the temperature distribution evolves. And so, for example, for a case where the pipe has some wall temperature, TW, and let's, for argument's sake, say that this temperature is 80 degrees C, and the fluid comes in at 20 degrees C. So there's a point downstream that this becomes fully developed. Now, at the point that it's fully developed, the statement is not that the temperature distribution in the pipe no longer changes. There continues to be a temperature distribution in the pipe, and so we have higher temperatures on the outside, lower temperatures on the inside, so we have a temperature distribution within the pipe. As we go further and further downstream, we still have a temperature distribution in the pipe, becomes much shallower until we know practically that as we go further and further downstream that eventually it's imperceptible what the temperature distribution in the pipe is, and it looks certainly like it's 80 degrees everywhere. Now, it could be fully developed, so this may be the point that becomes thermally fully developed, X fully developed thermally, and there's still temperature evolution downstream. What the Gretz solution, and remember that this Gretz solution is this separation of variable solution. So the Gretz solution is the separation of variable solution that tells us really the full variation of the temperature evolution in this pipe. And so it's this T of XR solution. And it says that once we are sufficiently smooth, that at some point we may, for example, just have a leading order term. So remember that under normal conditions there would be a bunch of other terms because it's a separation of variables series solution, and there would be lots of other terms that are down here. But as it gets further and further downstream, as we go to large values of x, we get this attenuation by the exponential term, and we lose those higher order terms. So if T minus TW over the initial temperature, so T0 is the initial temperature here, that 20 degrees, as we go further downstream, this is a reasonable approximation. And we've talked about what the bulk temperature looks like. The bulk temperature is an integral of the temperature distribution over the area, weighted by the velocity. Certainly, T itself is a function of x and r. So if we integrate out the r dependence in the temperature and the r dependence in the velocity, the bulk temperature is no longer a function of r, but it certainly is still a function of x. So the same functional dependence that T has in x, the bulk temperature also has in x. What that means is that if we were to non-dimensionalize the temperature evolution, the excess temperature T minus TW by the bulk temperature excess temperature TB minus TW, all we get is a function of r. Okay, it has to be independent of x for the reasons that we just talked about. We're dividing a function of x by a function of x and r by a function of x. It's only a function of r in this simple separable sense. Okay, so the idea of fully developed thermally, the definition of thermally fully developed is really embodied by this mathematical statement. So thermally fully developed, and I need you to know this definition, means that the non-dimensional temperature profile does not change with respect to downstream distance, x. and it's non-dimensionalized in a particular way, and that is in terms of the bulk temperature. Okay? Now, I say consider the constant surface temperature case. This is true for both constant surface temperature and constant heat flux. So we're going to talk about this for the constant surface temperature case, but it is much more general. So if we take the derivative of this T minus TW over TB minus TW with respect to R, so this is this non-dimensional temperature that is not dependent on X. So this thing is just a function of R. And we take the derivative with respect to R, then it's still just a function of R. When we evaluate it at a particular value of R, it has to be a constant. So no matter how complicated a function of R we have, if we evaluate it at a particular value of R, 1 centimeter, it now is just a number. So by constant, we just mean it is a number. But if we take this derivative, so we take this derivative with respect to R, we get dt in the numerator, we get dt dr at R is equal to R. In the denominator, neither T bulk nor TW, the wall temperature nor the bulk temperature, are functions of R. So we have that it's just dt dr at a particular value of R divided by TB minus TW, and that's also equal to a constant. Well, if I'm going to call that constant C. So C is equal to what we said here is dt dr at R is equal to R divided by TB minus TW. Well, what happens if we multiply this by thermal minus the K times the thermal conductivity? So we get minus K dt dr at R is equal to R over TB minus TW. I want you to notice that this is just the definition of Q wall. So the numerator is Q wall, and the denominator here is TB minus TW. What this says is Q wall is equal to minus K times some constant times TB minus TW. What we do is we associate this Kc as the heat transfer coefficient. So it says that the heat transfer coefficient is a constant as long as the thermal conductivity is a constant. So it says that for all the problems that we're dealing with in these problems of interest, when we're thermally fully developed, so it doesn't matter if it's constant heat flux or constant surface temperature, when thermally fully developed, H is a constant as long as we have constant thermal properties. And so this is pretty powerful. All right, and so the way that we use that is we just pointed out that what we really got out of this is Newton's law of cooling, and that we can identify H over K with this constant property. And so for the constant heat flux case, the same thing is true, that H is a constant, and there's just a slight modification in terms of what we see for that. So one of the things that we can get for the constant heat flux case is we're going to take the derivative now with respect to X of this non-dimensional parameter. We know that this is equal to 0 because, again, this is just the definition of being thermally fully developed. So thermally fully developed means the ddx of this quantity is equal to 0. We expand out the derivatives using whether you want to call it the quotient rule, the product rule, but the first term is we take the derivative of the numerator and we divide it by the denominator. Over here we multiply the numerator by the derivative of the denominator, and this is equal to 0. We continue expanding out the terms, so this is again the this is associated with the numerator. These first two terms are associated with the numerator, and the last two terms are associated with derivatives of the denominator. And so, assuming the Newton's law of cooling holds, and we know that by being fully developed, that thermally fully developed, that is, that H is a constant. So QW, which is HTB minus TW, is a constant. Why? Because, well, we said that it's a constant heat flux problem, so Q is a constant. We said H is a constant, so it already says something about TB minus TW. It means that TB dTB dx is equal to dTW dx. I hope you see that. So assume H is constant. When do we assume H is constant? If K is constant, so if it's constant properties. And if that's true, H TB minus TW is equal to Q, which is a constant. We take the derivative of this, with respect to x, we get 0, and it just says that dTB, it says that the bulk temperature, which we found to be linear for a constant heat flux problem, has the same variation as the wall temperature. So what that means is, take a look at the terms up here. It means that these terms, because dTB dx is the same as dTW dx and they have opposite signs, that these cancel each other out. And if those cancel each other out, it tells us, because this whole identity is equal to 0, that there's something we can say about dt dx and dTW dx. So what we find out, and interestingly enough, is for these constant flux cases, everywhere that we look, dt dx at all values of r, at all radial locations, the change in temperature with respect to x is always linear. It's always the same as, well, it's a constant because T is linear, TB is linear, TW is linear. The derivatives of these with respect to x are constants, and dt dx is a constant. What that means then is that, and we know in fact what the value of that constant is. We know that constant is defined in terms of the heat flux, the bulk flow, bulk velocity, etc. And so what it means is that when we look at the high Peckley number problem for a pipe or tube, that dt dx, this partial differential equation, is not so bad because this dt dx is just a constant. If it's just a constant, we can integrate this thing, including the radial velocity profile, and get the temperature distribution. Once we get the temperature distribution, which is really what it gives us really is a T of X profile, I'm sorry, a T of R profile. Then we find TB, and once we find TB, we find the Nusselt number. And the way we find the Nusselt number is, let's just define it sort of a little bit. We say NUD is HD over K, but really what that is we substitute for H. We know that H delta T is equal to minus K I'm sorry, R is equal to R, not D. And so we can substitute, which is just, again, our Q. So what we're really doing is we're substituting for this Q over delta T, where it's TB minus TW D over K. So we get our TB minus TW from our temperature profile, and we know what Q is, we know what D and K are. If we do that, we find that HD over K is equal to 4.364. And so this is an important result for problems of this type.